All right, here we go. So I'm going to talk about one thing that you guys will see frequently throughout stats and everything. And actually, like, there's 2 state standards for stats that are hit on really, really hard. One of which is correlation does not imply causation. And you guys know that already, right? If 2 things are correlated, doesn't mean one causes the other, right? The second one is the law of large numbers, okay? So I'm going to do my very best to explain to you how the law of large numbers works, okay? Here's how the law, and I'm going to use, I'm going to do, let's do children, right? Okay? So let's say somebody has 1 child, right? It could be a boy or a girl, right? So 1 kid, don't write this down. Okay, 1 kid, let's say they end up with a boy, right? So after 1 kid, here's how our breakdown is, right? Let's say after 1 child, boys, girls, we are 100% boy and we are 0% girl. That's about as split as they get, right? 100% to 0%, right? After 2 kids, okay, let's say we have another boy, right? What percent boy are we? Still 100% boy. How about what percent girl? Still 0% girl, right? Let's say after 3 kids, we finally have a girl, right? So we're boy, boy, girl at this point, right? What percent boy are we? 60, we'll go 67 and 33 if we round, right? 67 and 33, okay? That's what our split is, right? Let's say after 4 kids, we have a boy or a girl. What do you want? Girl, a girl again? Boy, boy, girl, girl. Now what percent are we? 50-50, okay? Here's what they say. They say the law of large numbers says this, okay? This guy right here is the experimental probability, okay? And she was 75-25, right?
What?
She was 75-25.
Yeah.
Yeah.
Weirdo.
Not 50-50, I don't know. I'm the same, but I'm the opposite of you. I had 1 boy, 3 girls, so I'm the opposite. This is the experimental probability. Okay, let's talk.
Oh no, my sister is weird because she now lives in Lawrence.
Yeah, she's like my neighbor. Kinda. We're all neighbors. Okay. Actually, she kind of lives across town, but I still call her my neighbor because, like, you know, whatever. We're all neighbors.
No.
Right. Okay, the theoretical probability. In theory, when you're talking boys and girls, what is the theoretical probability of getting a boy versus a girl, right? 50-50, okay? 50-50. Okay, so here's the law of large numbers. Listen, this is important. Listen. In theory, when you have a baby, 50% boy, 50% girl. That's your theoretical probability. But in experiments, like when you're actually having children, it may not always be that case, right? Like we went through the scenario of 1, and then 2, and then 3, and then 4, and then 5, and then 6, and you keep going, right? Okay? And I'm not talking just for one person, but like let's say like the School of Blue Hill, right? If we talk about all of the children in the School of Blue Hill, the law of large numbers says this. Ready? This is what the law of large numbers says.
Okay.
The more trials you have, or the more children you have, the closer this split, this percentage, should get to what the theoretical probability is. Does that make sense?
Yeah.
Like, when we only had 1 child, right, that was 100 and 0. Like, that's really far away from a 50-50 split. But the more we get, the closer that's going to approach what the theoretical probability should be. Does that make sense? Right? Like, you would be very, very, very surprised if I had 1,000 kids. Okay, like not me, right? You would be very surprised if we had 1,000 kids, like maybe in the School of Blue Hill, and my split was 600 and 400. That's still a very large split when you have 1,000 kids. True? 1,000.
I wouldn't know. I don't have it.
I'm talking about like in a school, right? Okay. It would probably be, if you had 1,000 kids, it would probably be closer to a 500-500 split, right? Because that's a very large number of children. True? Okay. So the more that number, the higher that number gets, the closer it gets to the split, right? Okay. So another example of this would be like rolling a dice, right? Yeah. What's the theoretical probability? I'll just say theoretical probability of rolling a 4. 1 out of 6, right? So, I mean, if you only roll the dice once, like it's probably not going to be a 4. If you roll the dice 10 times, maybe it's still not 1/6. But if I roll the dice, let me go, like 600 times, right? About how many of those times are going to be 4? about 100, right? Because it ends up being close to what the theoretical probability is, the larger the number of trials you get. Does that make sense?
Roll it 6
Okay.
times, you should get 4 of these ones.
Well, maybe,
Should.
Maybe.
He said should.
I
right?
said should.
Okay, but so let's play that out, right? If you, yeah, in theory, that's what should happen, right? But if you roll the dice 6 times and you don't get a 4, would you be like, oh my god, I can't believe I didn't get a 4?
Yes.
Yes.
You would?
Yep.
I wouldn't.
I thought it was-
If I rolled the dice 50 times and I didn't get a 4, then I would be like, holy moly, I can't believe I didn't get a 4. Does that make sense?
Yep.
So if I rolled the dice 6 times and I didn't get a 4, I'd be like, oh, well, that's kind of weird.
It's a
But if I
one
rolled it
die.
50 times, I'd be like, give me a lottery ticket, and I'm not going to put 4 on it, right?
No,
You
it's
know,
really
like
nice the way you talk.
like that's pretty strange. Okay, does that make sense?
You probably stole it, if you rolled it 50 times and you didn't get a 4, you probably stole it back from Vegas and stuff.
Yeah, probably, and it's like a shaved dice or something. I don't know. They do that,
Thanks, Chase.
or they weight them differently.
I only said that 2 times back here.
I just don't listen. I just don't listen to Jack. Oh, come on. I don't know why that's not going in there. Okay, whatever. I think our battery's okay. All right, so there you go. That's the law of large numbers. All right, let's go to example 4. Here we go. When 3 children are born, the sample space for the genders are as shown. Boy, 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 girl, boy, girl, boy, boy, girl, girl. If you put a split, put like a little line in between those two. The first 4 and the second 4. What divides the first 4 and the second 4? These ones all start with boy. Those ones all start with girl, right? Like that's kind of my way of organizing them, right? So there's 4 on each side, so 10 or 8 total. If boys and girls are equally likely, then those 8 simple events are equally likely to happen. So here's the deal. I'm going to list these off to the side. Boy, boy, boy. Boy, boy, girl. Boy, girl, boy. Boy, girl, girl. Girl, boy, boy. Girl, boy, girl. Girl, girl, boy, and girl, girl, girl. All right, here's the deal. Those are the 8 combinations that I could have. What is my chances if I have 3 children of me getting 3 boys in a row?
Probably not very high.
I mean, what is it though?
Mm.
What's my chances of getting all 3 boys in a row?
Like,
How many combinations
Well,
are there? How many combinations are there?
like 6 or 7%. Probably.
No. How many combinations are there? It's 1/8, right? I have a 1 in 8 chance of getting that combination exactly, right?
Oh.
I have a 1 in 8 chance. The combination that I had was this one. I had a 1 in 8 chance of getting that exact combination. Now, here's where it gets a little bit different, right? Okay. Let's say if I ask what's the probability of getting girl, boy, girl exactly. Okay. What is the chances of getting a girl, boy, girl combination exactly? That would be like this one right here. Girl, boy, girl. What's the chances?
Like
1/8,
probably
right? 1/8. But now let me ask the question a little bit differently. What's the probability of 2 girls, 1 boy? Okay, is that different? Yes. 2 girls, 1 boy is this combination 2 girls, 1 boy. No, is this 2 girls, 1 boy? No, is this 2 girls, 1 boy?
No.
No, is this 2 girls, 1 boy?
No.
Yes, this
But
one is
it's
2
not
girls,
the
1 boy.
order.
It doesn't matter.
It's hard.
When I ask it this way, I'm just asking 2 girls, 1 boy in general. I don't care what order they are. This one is noting the order. This one order doesn't matter. So 2 girls, 1 boy works here. 2 girls, 1 boy?
No.
No, 2 girls, 1 boy?
Uh-huh.
Yes, 2 girls, 1 boy?
Uh-huh.
Yes, 2 girls, 1 boy.
Uh-huh.
No, so what are my chances then of getting 2 girls, 1 boy when I don't care the order? 3 out of 8, right? I have my probability goes to 3/8 instead of 1/8. Do you see the difference? This one's asking in any order. This one's asking this specific order. Yes? Okay, that's what they're asking here. So it says find the probability of getting 3 children all of the same gender. Okay? How many combinations here have 3 that are all the same gender? 2. Either boy, boy, boy or girl, girl, girl. That is 2 out of 8 or 1/4, right? It's, oh, here it is. Here it is. In reality, the probability of getting a boy is 0.512 instead of 0.5. So it's like 51% boy. And that was as of when this book was published, which I have no idea when that was, like 2018 or something, I think is when this book was. So there's that. But do you see how this works? Okay. All of those, if they're talking about in any order or like 3 of the same gender, it doesn't matter. It doesn't have to be all boys or it could be all girls, right? So that's 2 combinations. Good?
All things.
Okay, example 6, texting and driving. Jace, will you turn around, please?
I'm listening.
No, turn around. You're distracting Jack. He needs to focus.
He's distracting himself.
That's what I'm saying. He has a hard enough time focusing without you distracting him, right? Okay, here we go. Example 6, texting and driving.
I love doing that.
In a study of the U.S., it was found that this many people texted while driving in the previous 30 days. They're throwing a lot of numbers out to you, but the 30 days means nothing, right? Okay, sometimes they will throw numbers out to you and you're like, what do I do with the 30? The 30 means nothing, right? It's just telling you information. And this many did not. So 3785 equals yes texting. 4720 equals no texting. They're probably lying. You're right.
I
Okay.
didn't text while I drove today. I left at Marketplace.
Oh my God, child. Oh, I don't want to hear that. Okay, based on these results, if a high school driver is randomly selected, what is the probability that they did text while drive? Okay, so how do I find out what the probability is of them texting while driving?
Yes over.
The yeses, which is 3785 over the total, and what's the total? 5015 8505. Okay, all right,
Yeah.
somebody divide those for me. It is a little less than 50%, right? 34.5? 44.5. Okay. 445. So you can leave it like this. You can write it as 44.5%. Which one do I want? I don't care. I don't care.
Me neither.
Any of them,
Me neither.
right? I wouldn't, because this is such a big, this is the fraction form and it's not reduced. I wouldn't leave it in fraction form. I would either move it to a decimal or a percent, either way, okay? But 44.5% say that they've texted while driving. Ooh, that's a lot of distracted drivers out on the road. And even so, I think that's probably higher than that, right? This was as of like 2018.
You're fine.
Oh my God, oh my God, oh my
Practice
God.
makes perfect. That's what I say, right?
I do the talk to text.
Oh my, you're one of those.
Sometimes I'm one of those, yeah.
I do the Facebook.
And then I end up sending a message where it doesn't make any sense, and then I'm
So
like,
you're
oh
old.
crap, Layla
That's
fixed
what you're
this.
saying?
Yeah, I'm old. I am old.
Yeah, we know.
Like I'm old. So the other day I was talking it was like in Calc or something, and Brady Carr. I was talking about like, oh yeah, back in my day, my senior year, we won the state championship in football, and he's like, oh yeah, the year that we were born. I'm like, oh my God. Oh my God. Don't tell me that.
You're not
So
even
yeah,
that
I'm that old. I'm that old.
You're pretty old.
Yeah. Yeah.
What are you? 96? That ain't
30, I'll be 35 in like a week.
That ain't even old.
It's old. I can remember my mom being 35 when my brother was born.
I can't.
Like, ooh, yikes,
I remember that.
yikes.
Die of fire, you piece of shit.
Hey, stop. All right, example 7. A and B, Thanksgiving Day. All right, let's test your knowledge of how you know calendars work. Here we go. If a year is selected at random, find the probability that Thanksgiving Day in the United States will be on a Wednesday, and find the probability that it will be on a Thursday.
Isn't it always Thursday?
So it's 100%.
So 100%.
But some of you guys were playing the 1/7 because Wednesday is 1/7. No, that entered Jace's mind. He doesn't know. So what's the probability? What's the? I know you don't know your days. Do you know that Thanksgiving is on a Thursday every year?
Brad doesn't know his days either.
No.
Okay, all right. I don't know. So what is A? What's the probability that it's on a Wednesday? 0%, right? Or 0 as a decimal, or 0%. What's the probability that it's on a Thursday every year? 100%. Or what's that as a decimal? 1, right? 1 is a probability, or 100%, right? Okay. So there's that. That just goes to show you can't have a probability be higher than 0 or higher than 100% or less than 0, right? It has to be in between one of those
Did you
two.
just have a stroke?
Good, good?
I think she did.
Probably.
She's about that age.
Okay, one of the last things is something called complementary events. Go to the top of the next page. Top of the next page. Complementary events. Complementary events are events that add to 100%. Okay, so for example, let's say they do this to you on the ACT a lot, but some of you guys are like done with the ACT. Please do not.
Excuse me.
4 blue and 5 purple and 6 green and 2 pink. Okay?
Had my hands ready.
How many? For one thing, you should be adding these all up because that's one of the things you're going to have to do. How many is that?
17.
17. Okay. What is the probability of blue? Blue.
4 out of 7.
4 out of 17. Okay. What is the complement of blue? Nope. Nope. Nope.
Orange.
Everything else. What would everything else
You
be?
get an orange.
Probability of
13.
not blue. That's the complement. What's the probability of not blue?
It's a 13.
It's 13. How did you find out that was 13?
You add up everything else but blue.
You just
Well, don't
subtracted
add them all
4.
up. I would subtract the 4. I do what Jace does. I don't add them all up. I subtract the 4 from 17, right? So 13 out of 17. These two are complementary events. Okay, now, here's the notation that they will use. Is everybody listening? Because you're going to get confused, and on the homework, you're going to be like, what does this mean? Probability of blue, they might call that P of A. They might call blue event A. Okay? Not blue or the complement, they will call it P of A bar. Okay? A with a bar over it is the complement, right? So if they say P of A is blue, P of A bar is not blue. Yeah? Okay? That's the notation that they use right here. Circle that. P of A bar, those are complements. One of them is blue, one of them is not blue. One of them is dying when you skydive, one of them is living when you skydive. Okay, that's what we're going to do in example 8. Okay, so dying and living, those are complements of each other. Because there's no in between, I think. I don't know. Anyway, example 8.
Coma. You could be brain dead.
But you're still living.
But
I don't care.
brain's dead.
You're still living.
But what happens when some people like flatline for a while and then they come back?
I was brain dead at the Elm
I don't
Creek
know.
game.
Yeah, we know.
I don't know.
But you don't even know.
I don't know. All right. Okay, so example 8. Example 3 showed that in a recent year, 3 million skydivers, 21 of them resulted in death. Find the probability of not dying. Okay, so let's say P of A is equal to P of dying, which would be 21 over 3 million. So they are not asking for that one. That would end up being like 0.0, I don't know, remember how many zeros. Does somebody look back? 5 zeros and a 7, right? Point 1, 2, 3, 4, 5, and a 7, yeah? Okay? They want P of A bar, and what will A bar be? Probability of
5 nines.
live, which is the other whatever amount, right? 2, 9, 9, 9, 9, 7, 9, right? Out of the 3 million, okay? Or Rem's like, let's just go and let's subtract that. If I subtract that from 100%, this would be 0.9999993, right? That's the probability of live because these two will have to add up to be 1 or 100%, right? That's the probability. They will call them A and A bar. Those are complements of each other, okay?
Gotcha.
They add up to be 1. Good?
Wait.
I'm waiting. I don't know. She's writing it down.
Jack's not even writing anything.
Yeah, you should be writing
I
this down.
never do.
Yeah. Okay. Okay. Just keep in mind, this is a college class, by the way.
Yeah, no.
Like,
If we
be
pay,
prepping. If you pay, yeah,
It's
sure.
not just the second semester, too.
It's you have to take it the whole year, but it counts for the you get credit for it for the second semester. Because
Yes.
if you were to take this class in college, it would be I don't know, 5 hours a week, but it would be 3 days a week. Does that make sense?
Yes.
So it would be 2 hours, 3 days a week or whatever, which is the same length as what our whole calendar year would be. Does that make sense?
Sure.
Yeah, sure. Okay. All right. Anyway, so that's how they do it. All right, here we go. Ready? Significantly high, significantly low. This is another thing that's very, very frequently tested on. This might be the last thing I talk about before we do odds maybe tomorrow. Okay? Significantly high, significantly low. We've talked about these before when you're doing a number line. Okay? What goes in the middle of your number line?
probably the middle.
0 as a z-score, but it is the average, right? The average. How do you tell where a significantly high cutoff and a significantly low cutoff was? After 2 what? 2 standard deviations. So whatever your standard deviation is. Let's say my average is an 80 and my standard deviation is 5. What's considered to be a significantly high score?
Anything over.
Anything over
You got it, buddy.
90. Anything lower than what is considered a low score? 70, right? That's 2 units of standard deviation. Now, here's the deal. They will say this. Now and we're not changing the rules because they all align with each other, but here's the rules. When it results in probability, it is considered to be a rare event if the probability equals, I'll just say, if the probability is less than or equal to 5% or 0.05. Okay? It is rare if the probability of that happening is less than 5% or less than 0.05. Yeah? Okay, now, that does align with what we're doing over here, right? Here we did 2 standard deviations. What percent of your data should live within 2 standard deviations according to that one rule?
A lot, like 90 some.
95%. So it is considered rare if it is outside of the 5% mark. Does that make sense?
Yeah.
Okay. So if the chances of me doing something is only 3%, is that a significantly
What?
rare event?
What?
Okay. If the chances of me doing something is 3%, is that a significantly rare event? 3%.
Yes.
Yes, right? It doesn't really matter if it's on the high end or the low end because it's 5% no matter what, right? Because 5% lives on the outsides, right? Those 2 little tails add up to be 5%, right? Okay, so it is a significantly rare event if it is a less than 5% chance of happening. We're gonna relate it back to 5% a lot. Okay, so here they have a little bullet point. It says among 100 births, 75 girls is considered a significant event, a significantly high event, because the chances of getting 75 girls and 100 births, that's a pretty good split, right? 75, 25. The chances of that happening without intervention is 0.000, that's 6 zeros and a 3. Okay, we relate that back to 5%. Is this number less than 5%? Yes, so, yes, it is significantly rare, or in this case, a significantly high number of girls. Does that make sense? Okay. All right. Among 100 births, we had 55 girls. The chances of getting 55 girls was 18.4%. This guy right here. Is that a rare event to happen? No. 18.4 is less than 5%. So, not a rare event or not a significantly high number of girls. Does that make sense? Everything's related back to the 5% number. Okay. All right. Probability review before we get to odds. I'm going to wait. Do we wait and do odds till tomorrow?
Yeah.
Because we only have one. Okay, whatever. All right. Probability review. Here we go. The first bullet point. The probability of an event is a fraction or a decimal number between 0 and 1. Cannot be outside of those numbers. Can you have a probability be 0?
Yes.
Give me something that's a probability of 0.
Jace not being a girl.
Thanksgiving on Wednesday.
Jace not being a girl? Okay, whatever. What? Thanksgiving being on Wednesday. Sure. What's the probability that's 1?
Buddy.
Thanksgiving being on a Thursday, right? The one that we just saw, right? The probability of an impossible event is 0, right? Probability of it being on a Wednesday. The probability of something that is certain to occur is 1. 100%. It's going to be on a Thursday, right? Okay. The notation PA is the probability of event A, like P, probability of selecting a blue marble. P of A bar is probability of not selecting a blue marble, right? Okay. That does not occur. Okay. P of A bar. That's the complement. These two should add up to be 100%. Good? Questions about that?
No.
No. Okay. All right. Do your homework.
Can I use the restroom?
Sure. Sure.
Kevin, I'm gonna
What?
poop my pants.
No, you're not.
Just come
Yeah.
Okay.
Hey, Dylan.
And you should be able to do like a bunch.
Bubby.
It's still here.
You should be able to do everything except like number 42. So you guys got like 2.5 pages of homework. That's a lot. That's a lot. Okay, goodbye.